Right. This is a project that I've been discussing with many people at Flatiron and also in Stuttgart and in CISA and in Nuremberg, but the main players have been my PhD student Niklas and my postdoc Lorenzo, especially for the first part. And the second part, in which I'm gonna be discussing the slave rotor results, there we have been profiting from the insight by Daniele Guerci. So these papers have been, the initial communication just came out, and the other one, we are about to post it on arXiv. So let me try to start from a bit of general motivation. So how we classify topological band structures. And for that, we use symmetries. And for instance, if we start from the simplest absence of time reversal and particle symmetry, like Chern insulator, you see in this two orbital subspace denoted by this vector D, where I can write this Hamiltonian, that I can distinguish between the case in which the D vector, which essentially points from the blue to the red orbital, winds around the whole unit sphere, or only incompletely does that. And so that's a topological phase transition, and the Chern number changes. If I add a time reversal symmetry and consider two copies of that, I have a quantum spin-hole insulator, and this transition can be obtained only by closing and reopening the gap. So this classification gives us information about the metallic boundary states, the gapless boundary states, and is based entirely, as you see, on single particle eigenfunctions. Attempts to include interactions in this picture have been done in single-side DMFT in the framework of the so-called topological Hamiltonian, which, however, is limited by the fact that the self-energy is K-independent, of course, in single-side DMFT. And there have been recently more sophisticated constructions based on two-particle symmetry indicators that, however, are quite complicated to handle. So in this talk, what I'm gonna do is to try to go, let's say, on the other side, in the Mott phase, where we have a large U gap, but still keeping a simple description. And essentially, I'm gonna ask the question, what survives of this classification in Mott insulators, where we have lost completely the knowledge of single particle Slater determinants as eigenfunctions. So the main question is the topology still encoded in the single particle Green's function G? And for that, we can already use the extension of the winding number proposed by Volovic and Zhang and Gurari also, where the symmetry between the Green's function and its inverse is already manifest. You see this object here, some higher dimensional extension of that, are integers, are winding numbers, so they cannot change if you make smooth deformation of the Green's function, and extend to interacting cases the topological invariants. And you see that obviously the Green's function here, the poles can change this number, but also the zeros. And for that, you need obviously a momentum dependence of the zeros, namely something that goes beyond DMFT because is associated to a momentum dependence of the self-energy. So a back of the envelope Green's function for calculation for the atomic limit shows that you have a spectral function made of two poles like this, and the self-energy that is associated to this has to diverge as 1 over omega. So if we think that, so it's essentially we associate the Mott gap with poles of the self-energy differently from band insulators in which there is no self-energy, and so there cannot be a zero of the determinant of the Green's function, more generally speaking, but only a zero of some diagonal elements of the Green's function. So I'm going to show in the rest of the talk essentially determinants of Green's function that are good ways of showing poles of the self-energy. And the assumption that I'm going to do now is essentially that this single pole of the self-energy of the atomic limit remains even in the, if we go away from the atomic limit, but we stay with a large hard gap, remains an isolated pole. And since there is no imaginary part of the Green's function in the gap, there cannot be an imaginary part of the self-energy as well. And so the chance that this remains an isolated pole is reasonable, let's say. And so we can write the Green's function as a sum of 2 poles, obviously now momentum dependent. And if we recast this in the terms of the self-energy, essentially we end up with a self-energy that we can expand in T over U. And the claim that I'm going to make is that an expansion in T over U yields for this self-energy a form that looks like this, in which you have at the denominator a momentum-dependent dispersion, which is exactly the non-interacting one, but with renormalized parameters. Now here I have made 2 assumptions. The first one is this 2-pole approximation, and the second one is this T over U expansion. Both we are going to sort of test and extend in these 2 ongoing projects, which I would like to mention. The one is with Thomas and Mario using the composite operator method introduced by Adolfo Avella, which gives a systematic way of going beyond also the 2-pole approximation and check what happens to this isolated zero of the Green's function beyond that. And the second one is a nice physical interpretation of this form based on the D3-lex by Xenia and Mary. So now I'm going to use essentially this self-energy that you see here to show the consequences of that. But before we do that, let me just justify a bit with why we get this H0 tilde. That is my way of denoting the renormalization of the parameters. And this is quite transparent if we make a 1 over omega expansion of the self-energy. So by doing this from the beginning, for instance, starting from an upper model, you get an expansion that at the second order in 1 over omega contains something that is essentially a 4-point function with different sites. L and J are different sites, and convoluted, let's say, summed with the original dispersion. And this sum over Q essentially selects from the non-interacting dispersion the proper hopping bonds that go into the renormalization in the form of some correlation function, for instance, some W occupancy involving the 2 sites where you are considering the hopping. That's how you build this H0 tilde, that resumming gives you the denominator that I was talking about before. This has been already introduced in other papers, one by Achim Roche by solving a 2-orbital model that you see here, this essentially this H0 tilde popping up here, and a beautiful paper by André-Marie Tremblay, where he works out the entire continued fraction here, and this would be the same term that I'm considering here, and the lower floors of the continued fraction would not contribute if we make the limit T over U very small. I want to mention also something that is now quite popular at the moment, which is the Atsugai-Komoto interaction, which is a particularly strange interaction in terms of physics because it's a infinite range and entirely local in K, as you see here. This is, however, nice analytically because it allows to get some analytic results. In particular, in this case, this one floor expression that I have the self-energy would become exact. But that's just because of the specificity of this model. Anyway, the consequences of this H0 tilde allows us to classify Mott insulators. More precisely, if we call G tilde the Green's function in which we add our self-energy with the ansatz that I showed you, then the winding number of G can be shown to be the opposite of the winding number of G tilde. So essentially, we can say that H0K, the original H0K, and H0 tilde gives us the same topology, so they belong to the same symmetry class. We cannot change symmetry class with this single particle description, contrary, for instance, to these two particle indicators that I mentioned before. So we are restricted to remain in the same symmetry class. However, we can very easily analyze the topology of a complicated non-perturbative Mott insulator via the dispersion of its zeros. In particular, if we have a non-interacting band structure that has a winding number and some gapless edge modes as shown here, we have to sort of go in the Mott phase and calculate H0 tilde, and then we will have this red surface that you see here, and suppose that this parameter, this renormalization does not make the red poles, the red zero, sorry, trivial, then we will have gapless edge modes also in this case that of course are gapless edge zeros. So the bulk boundary correspondence extends also to the zeros and to this H0 tilde that we have to calculate, but in principle is possible with some numerical techniques. In some sense, we have access to a so-called topological quantum chemistry, but of Mott phases. But even more interestingly, we can then study the physical meaning of the zeros that has been suggested, for instance, recently by Michele in this beautiful paper. Not only this one, there is also another one suggesting the physical properties, the physical content of the Lattinger surface, and its excitations. And in the second part of my talk, I'm gonna discuss the link between H0 tilde and the spin-on dispersion. So let me start to illustrate what happens in an exactly solvable one-dimensional chain. So I take an SSH chain like this, and here we have a winding number that we can define again from our vector D, whether or not it encloses, encircle the origin of the plane. And let me show this determinant that is, as I said, a good way to show isolated poles. This is essentially resembles the spectral function. It's close to the spectral function. It's not exactly a spectral function because it contains sort of the real part of G, but it gives here clearly two bands in the weak U, the small u limit, but in a large U, it gives some upper bands here and here, and then topological zeros described by our H0 tilde. The topological invariant can be calculated either fully from the Green's function or from the winding number of H0. And of course, now the question is, what happens if we cut the chain? This was a cluster DMFT result. Now I instead do exact diagonalization of my finite chain. And again, I show something that is close to the determinant, but is spatially resolved. So these are now sites from 1 to 12 in my chain. And you see that I have, for the topological phase of this SSH model without interaction, some bulk eigenvalues, 1 and 2, and zero energy, zeros at the ends, at the two ends of the chain. Now, if I go to the interacting case, I switch it to the interacting case, then I have some bulk eigenvalues that are lower and upper rubber bands, essentially. And now my determinant shows nicely zero energy zeros that are in red here, isolated zeros, leaving at the edge of the shades at site 1 and site 12. So now what I want to do is to glue these two chains together in order to let this guy here speak to the left here in a non-interacting chain. So I have half of the chain interacting and the left half non-interacting. And what happens is something interesting. Now this is from 1 to 12 again, but you see I have a zero energy pole at the very left, a zero energy zero at the very right, but at the center, I lost the isolated zeros. So the chain does not have isolated zeros in the center, which somehow is reasonable from the point of view of topology, because if the two systems have the same topological index, there cannot be an edge, a gapless edge state or boundary state in the center. However, this suggests that there is a mechanism to hybridize this guy here with some low energy states that is close by. And this can be understood even better if you go to the spin language, if you switch to a spin language in which this SSH chain essentially has a spin gap, which goes as j to the, of this delta j to the 2/3. And you see that in the non-trivial case, with open boundary conditions, the spin gap is 0, meaning that we have isolated spins at the edge of this SSH chain, suggesting that this hybridization is nothing but some kind of screening of this isolated spin with the bath coming from the metallic part of the so from the non-interacting part of the chain. In 2 dimensions, we can do the same, and in classical DMFT, we can see the inversion of the of the bulk zeros by changing M, as shown in this picture, and classify again our topological Mott insulators via H0 tilde or via the Green's functions, just integrating brute force them. And if we make a slab of that, the determinant again will give edge poles for u equals 0 and edge zeros in the Mott phase. You see here where you have upper and lower rubber bands, and then in the center, this gapless edge zero. So now the interesting thing is to see what happens of this annihilation in 2 dimensions. And if we interface a conventional TI with edge modes like this, with this new topological Mott insulator with edge zeros, and then we follow a wave packet that propagates following the Green's function from this side. So I'm essentially following a wave packet that should propagate on the edge if there was no topological Mott insulators. And from this point on, I will let instead this wave packet speak to the left, to the edge zeros of the Mott insulator. And essentially what I see is this blue Gaussian packet package that loses weight when it can speak to the zeros of the topological Mott insulators, which is a paradox, of course, because it seems that I lose my original electron when there is the possibility for it to speak to the edge zeros on the other side. So to understand this kind of apparent loss of charge conservation, we looked at the Kane-Meyle-Hubbard model and solved that with the slave rotor methods introduced by Antoine and Serge Florence. And essentially here, we go to the large M limit and solve the rotor quantum sigma model equations. And in this case, we find, as already found by Stefan Rachel and Catherine Lehour, a gapped U1 spin liquid in which we have bulk spinons that are inverted and edge spinons that go around our sample with instead a charge sector that is gapped. This is also similar, is actually very, very close to what pacing and balance found in this 3-orbital model in which the spinons have an inverted band structure in this topological Mott insulating phase that they find here before magnetic ordering sets in. And so here, now what Niklas did together with Daniele was to study this now in real space, kind of in real space resolved geometries in order to study the interaction of these edge spinons with conventional edge states of TIs. And this is the dispersion of the spinons, so linear dispersion of the edge spinons, and the bulk you see here and here in a slab calculation. And now Niklas suggested this nice torus geometry where we can see very nicely the annihilation. So what happens is, again, we have half of the system that is with large U, so a topological Mott insulator in this sense, so this gapped U1 spin liquid, and on the other side instead the conventional TI. So now here I will have normal edge modes, and here edge spinons. And this is their spectrum. So the green are the TI on the TI side, you see here, and the blue are instead the edge spinons here. And if I now let the two speak to each other, so these are completely decoupled, they have different velocities, you see, but if they speak to each other, now they can annihilate like in this case, and indeed we find a gapping out of this edge spinons. It's essentially kind of a condo insulator gap that opens up because these spins get screened by the conduction helical boundary modes of the TI. And of course, this is what happens to the spinons. I promised I would have told you about the connection with the zeros. To get to the zeros, we have to perform a convolution between the rotor and the spinon Green's function, and if one does that in the bulk now for different values of the spin orbit coupling lambda, once it has a picture like this. So we have upper and lower upper bands. Now in this solution of the slave rotor, the nice thing is that we have spatial fluctuations, so our zeros have a dispersion, contrary to single-side DMFT. So this goes beyond single-side DMFT. And you see that the red dispersion here is the zeros. And in the dashed black line, I show the spinon multiplied by a factor of 10 in this case. And if I now progressively reduce lambda, so the spin orbit coupling, you see that I get close to a situation in which the two become gapless in the bulk at K and K prime and invert their dispersion at the same lambda, which in this case is lambda equals to 0. So the spinons and zeros are not on top of each other in terms of excitations, but their topology is the same. And this allows to address or to solve, if you want, our strange destiny of this wave packet that was shown before, now recasted in this honeycomb geometry language. This would be like this, that we have a wave packet flowing here, and then when encountering the zeros on the other side, that we were not sure what was going on at the interface. But if we now show this in terms of this charge gapped rotors on the Mott TI side, where only spinons flow around, and instead in the conventional TI side we have condensed rotors, so no spin charge separation, then it's clear that what is going on at this level here will be that the charge remains confined to the TI side, whereas the spin-on goes around the whole sample. So here we were not seeing the physical electron because essentially this macroscopically phase separates in a way that the spin-on travels further all the way around the topological Mott TI, the topological Mott insulator, whereas the charge remains here in the TI side. And this is consistent with the Joffe-Larkin composition rule that you can work out in this case where we have where we have a system with spin charge separation like this, because if you have uncondensed rotors, so a gap, then you have zero conductivity for the boson, and the conductivity from here to here is given by the original conductivity of the C fermions. Whereas if we now make both sides with condensed rotors, so we are essentially interfacing two TIs, then the conductivity of the boson becomes infinite, and this compensate perfectly because here this disappears, and we have compensation between sigma C and sigma F, and so no edge transport as it has to be in this case where we have essentially a conventional TI in the whole system. So this in some sense gives an answer to the puzzle that we were finding in the first part, where we were not considering in our wave packet explicitly the possibility of spin charge separation at the edge, and opens, of course, a number of interesting questions like how exactly this scattering here happens, and what happens to the other spin copy, because here I'm always showing just the spin up sector. Of course, there is also a spin down sector, and so there is backscattering at the interface, and what happens to the charge when we have the other spin. So a number of open questions that this spin that is slave rotor formalism has actually shown us in a beautiful way. So let me just summarize, because my time is essentially up. So that's the bulk boundary correspondence for the bulk zeros that give rise to gapless edge zeros in topological Mott insulators. We have shown this annihilation between zeros and poles, in some sense resembling a Kondo insulator mechanism, and found spin charge separation at the interface between a conventional and a Mott topological insulator. Thank you very much.
Thank you very much, Giorgio. So we are now open for questions. So please, if you have a question, just raise your hand. We're gonna unmute you. You can also use the Q&A or the chat. There's a question in the Q&A. Gabriele. So Gabriele, I will unmute you so that you can ask your question yourself.
Am I supposed to hear something?
No, I don't think, Gabriele. Okay, so I will read the question. As far as I know, the original claim about the Meillet-Hubbard model having a quantum spin liquid phase has been debated a lot. The argument being that it could just be a spurious find due to finite size effects in the original quantum Monte Carlo simulation. How much these results rely on the quantum spin liquid picture? Do we need to interpret the green function zeros as spin-ons? And finally, do the new slave rotor calculation give some insights on the old quarrels?
Yeah, so that's a very good question. So if you want, what I'm showing here is slave rotor mean field result, which means that I'm not considering at all the fluctuations of the gauge field beyond that. So that actually this is not going to solve that in terms of stability. So if essentially this gap D1 spin liquid is not stable, then beyond mean field, beyond the saddle point, then things will be more complicated. So that is in some sense a partial. So the slave rotor, I see the slave rotor as a nice way of linking the zeros of the Green's function that we have been discussing recently with the established understanding of spin-on in quantum spin liquid. So that's somehow a link that we make. They are not the same as I showed, but they have the same topology. That's the point. Yes, there are further.
Thank you very much. Yeah, so Michel, you can ask a question. We'll unmute you. Oh, no, okay, sorry.
Okay, can you hear me now? Yes?
Yes.
Thank you for the nice presentation. So I do have a question on the SSH model. When you join the two SSH together, yes, that's you going there. You demonstrated that when they have the same topology, that is interacting or non-interacting, then the states interact with each other and they open a gap. I was wondering if it's a different topology, let's say on the non-interacting, like dimerized the other way, do you still, do you form a polaron at the interface?
So what the statement here is that if they have the same, if they are in the same topological class, and if they have the same non-trivial number, value of the invariant, then they will hybridize. So I cannot answer to the question whether you have a completely different interacting kind of topological class. Imagine you form a completely different state on the right. Then in some sense you don't have the same topology left and right, and in that case I would expect everything can happen. No? So this gapping out, this is just a way of the system to avoid that here you have a gapless zero that is not allowed in this, if left and right you have the same topology at the single particle level. If you're asking whether at the two particle level I can have something more complicated, then left and right can speak differently to each other, yeah.
No, my question was simpler, is that like the topology comes from the dimerizations, the way the dimerize. So if you switch dimerization,
if I switch dimerization, no. Then in that case, then I would have a z. Well, in this case, it's n1 equal 1 and n1 equal 0. And then in that case, I don't see annihilation.
Okay.
I do see annihilation, however, even if I break. Because you might have noticed that I show here perfect particle symmetry, even though there is no need of particle symmetry in the SSH model, I still observe annihilation even if I remove particle symmetry, only that it would not be as clean as here because I mismatch the two, and then this annihilation becomes less visible in some sense. Yeah.
Thank you.
Yeah.
Okay, thank you. We now have Irakli.
Hi, thank you very much for nice talk, Giorgio. I have one question. As I understand these results, it's kind of continuation of previous question, was done with exact diagonalization. what do you think, how much the finite size effects plays role, and what happened if one consider a larger system?
Yeah, so for the one-dimensional chain, we solved that because essentially already in the first paper, this is now pretty small what I show here, but Marcel Clet performed a Monte Carlo calculation with as far as I remember, 48 sites or so, and there was everything that we find at the level of ED was found also there. For the slave rotor calculation, we have finite size effects, but in a trivial way in some sense. I mean, it scales not fantastically because we have not optimized it yet. But we don't have the same exponential growth as here. So that for the slave rotor part is not an issue, I would say.
I see. Thank you very much.
Thank
you. Perhaps one question also, Giorgio, elaborating on Gabriele's remark.
Yeah.
So would you agree with me that when we do slave rotors, the question of whether the model has a quantum spin liquid, perhaps of U1 nature, is a little hard to answer, because one would, I mean, of course, the slave rotors are naturally prone to generate such a phase, right? And with a spin on Fermi surface, or perhaps Dirac points in this case. But in fact, one would have to study competing magnetic states and things like that, right?
Yeah, absolutely. So magnetic states and also fluctuations beyond that. Somehow, I was already very happy to get a dispersion of the zeros in this model, as it was not completely clear at the beginning to me, because many other slave formalism have flat zeros in the Green's function, whereas the slave rotors are particularly suited for giving that.
Yeah, and this is because you solve the effective sigma model in finite dimensions, right?
Exactly.
So you give a dispersion to everything.
Exactly, it's what you call this better mean field kind of solution. Exactly. Now, of course, the next step would be going beyond that, as you say, and study the stability of that. Yeah, I think that in the spin liquid community, the stability of gapped spin liquid is less debated that the stability of gapless spin liquid, but that's still yeah.
Okay, thank you.
And yes.
Thank you very much. Now, next we have Andy that has a question.
Now, am I unmuted?
Yes.
Yeah.
Great. All right. Sorry. Okay. Just further to Antoine's comment. I mean, while it's certainly true that one may question the accuracy of this kind of mean field slave rotor approximation for determining the true ground state of the model, to me, it's important to, in Antoine's favorite phrase, separate variables a little bit. I believe that the accomplishment here is drawing a link between a spin liquid ground state, which was explicitly constructed, Green's function zeros, and this interesting behavior at the edge, right? And the important question on the table here is the validity of that link beyond the mean field slave rotor approximation. Of course, if the ground state is different, then there may not be Green's function zeros, there may not be topology, et cetera. That's a different question. So I'd like to ask the assembled multitudes, is there a reason to be scared of the slave rotor approximation for those particular questions? That is, this constructing the edge state and how it annihilates and so on.
Oh, I mean, maybe I can make a comment on that. I think as long as we, as you mentioned, place ourselves in the framework of this quantum spin liquid phase, this is probably a quite economical approach that is fairly reliable in the sense, provided one does this improved mean field that solves the rotor model in finite dimension as was done.
Yeah. Yeah, what Niklas here together with Daniele did was this finite size kind of solution, but
yeah.
the quantum nonlinear sigma model is solved in finite dimension, so that's how we can get this dispersion of the zeros, and yeah, it's still very, I think what is the difficult question, Andy, we discussed a couple of times, is how this connection, this link between the zeros and the spin-ons survives, extends when we dope, or at least we move the chemical potential and we start to get into the bands. Then we have to work a bit more. As long as we stay in this perfectly particle symmetric situation, the link is very clear. But the evolution with chemical potential is more tricky, and we have to, yeah.
Well, if I may say, yeah, sorry, Giorgio, please.
Yeah, no, I would say it requires some more thinking than, or at least something more than what I was showing in this talk, where I didn't address this at all.
Well, I think Niklas has, I think there, if one is willing to accept the spatially inhomogeneous slave rotor mean field theory, which is, really Niklas' big and Daniele's big technical accomplishment, then that question is clearly answerable. Again, the question is what goes, if anything, will go wrong with this theory on the qualitative level, will go wrong with the theory.
Yeah.
And Giorgio, just so that I understand things properly, so you're saying you're getting a gapped spin liquid?
Yeah. So the
fully gapped.
For every, well, you have the charge sector is gapped.
Of course.
The big gap, and then you have the spin-on gap that is ruled by this spin orbit coupling. And so if
I see. Now I get it.
Okay. If lambda is finite, you get a gap at the K point, and then lambda equal to 0, you get this gapless.
Okay, thank you.